Hey everybody, and welcome back to Algebra 2 Online. So the plan for today is to learn our last technique that we use to help us find roots for basically higher order polynomials. And just to start off, I kind of just want to do these two kind of quick little concept questions. But so the motivation for these is really just to make sure we're kind of clear on how imaginary roots work with polynomials, basically. So if I said write down a polynomial which has at least one imaginary root, I would kind of hope you think of stuff like x squared plus 1 or something. It's like a really classic example. And this, just a quadratic shifted up one, has roots of, plus or minus I. And the next question is kind of related to that because it says if a polynomial has imaginary roots, what is the minimum amount of imaginary roots it could have? And really, it could be 1, okay? But most of the time we're assuming in this class that A, B, and C are real numbers, that they're not, this is a symbol called the element symbol, but basically it means that A, B, and C are in this set of numbers. That if those things are real numbers, if you do like, 2x squared plus 7x plus 13 or something, whatever numbers you want to pick here and here and here, if you make those real, then it will have basically a minimum of 2. So if A, B, and C are real numbers, then your minimum is 2. And the reason is just because, when you do things like the quadratic formula, right, and you have like negative b plus or minus, the only way you're going to get imaginary roots is if that thing is a negative down there. And as soon as that's a negative, right, then you're doing plus and minus it, which is why you get a lot of things like this. You get like, actually there's a fancy word for this too, and it's called complex conjugates, but you learn more about those in pre-calc. But basically these two things are kind of like the structure that we typically see. It is definitely possible that you could have like, 2i or something in there, and then this whole thing could be thrown off. But assuming that doesn't happen, okay, if you assume A, B, and C are real numbers, then the minimum amount that you should kind of be used to is 2. So this is the Rational Root Theorem, and it's a very useful, very important theorem in Algebra 2. I'll just read it to you. So it says that if you have some rational root, p over q, is rational root of some polynomial f of x, then p basically has to be a factor of the last term, and q has to be a factor of the first term. Okay, so p, the thing in the beginning, comes from the end, last term, end, and then the thing at the end comes from the beginning. And that is assuming that f of x is written in standard form. So like, meaning like your highest order, polynomial starts with the highest one here, and then it goes down to the number at the end. So, it would not be that way if you said, the same, like this is also y equals 10 plus 3x cubed minus 4x. Then it won't work, okay? But if you write it in order, so from biggest to smallest, right, then this works. And I will actually show you why this works. But what I just want to do here is make sure you kind of see what this is saying. So it's saying if p over q is a rational root. So it might not be a rational root, right? But it's saying that any rational root you have comes from this like pattern. And rational numbers, right, are just, even 3 is a rational number. It's just over 1, but it's basically anything you can write as a fraction. So a lot of numbers are included in this. Sometimes students kind of forget that those are rational numbers too. But if I do it for this example right here, p over q, p is the factors of the last term, so 10. So 1, 2, 5, 10. and then q is the factors of the first term, so 1, 3. And you can definitely be plus or minus. So, you can think of getting to 10 as negative 2 times negative 5. So you basically can let any of these be positive and negative. And if I won't always do this. A lot of times I'll write it just like this, but here I'll kind of write them out too. So if you go through all those combos, what I'm basically saying is that you could have 1 or negative 1. Right? You could have 1 over 1 or like negative 1 over 1. Then you could have like 2 or negative 2, right? Again, just do like 2 over 1, 2, or negative 2 over 1. So you can do those, and we could do 5, negative 5, you could do 10, negative 10. Those are kind of all the nice ones, right? Those are actually all the integer ones. And there's 8 here, and then that's just putting these over 1, and then you could put all these over 3, and so you get another 8. So you could have a third or negative a third. You could have 2/3 or negative 2/3. You could have 5/3 or negative 5/3, and last 10/3 or negative 10/3. And so there's 16 total, and these are just possible roots, right? Make sure you realize that's possible. I'm not saying that these are all roots, right? This thing, x cubed, will only have 3 roots. So you're not going to have 16 roots like this. I'm just saying that if this has a rational root, then it will come from one of these down here. You could also have like all 3 be rational roots, and all 3 would then be found in here. So any rational root of this thing is going to be part of this set of numbers, or these 16 different cases here. So that's what the rational root theorem says. It says it gives you a way to kind of check for what a possible rational root would be. Then you'll have to do some kind of math to figure out if it is a root or not, and that's the next thing I'm going to talk about. All right, so this first part, how could you test whether something is a root or not? By far the easiest way to do this is to just literally plug the number in and hope, we'll say, for 0, right? So if you were checking that one of these things is a root, you might just go and like plug in 5/3, here or something. And if you plug in 5/3, you can just do that all in your calculator or something. And you get 0, you're like, okay, cool. That one's a root. I know that one's a root. So here I'm talking about 1/2. But so say then that we find that 1/2 is a root, then what could we do next to reduce the problem, like using that, and make it easier to find the rest of them? And this is hopefully also kind of clear. We would do synthetic division. That's basically the main reason I teach you synthetic division. That's the idea with it, right? We have this number in the corner, and then we have like those coefficients. We bring one down, right? So there's some sort of number here. But when we do this thing out, right, if we started with like an x cubed in the last problem here, then this will be an x squared, and we'll have like reduced the problem down. And then now you can just like solve this thing with like, factoring or like quadratic formula, something like that. But that's really the power of synthetic division. It's going to let you reduce any sort of problem you have here down a degree using that root, and then we could just keep going. And last question, how do you know when to stop? Well, basically you stop when you have n roots for some x to the nth kind of polynomial, right? So we know that there's that fundamental theorem of algebra, and here if it's x cubed problem, we would basically have to find one root and then do synthetic division. Then you're going to get 2 more out of the quadratic that you get as a result of that, and then you'll be done. But that's basically the plan for rational root theorem, is like find your contenders for roots, plug them in, and you just plug in until you find that one works. There's no sense in like keep going. That's like you know, there might only be one of these 16 numbers as a root. So why are you going to waste time and like keep trying to check all the other, right? So once you find one, then you just go and you chug through the synthetic real quick. And then after that, you know, you'll have an easier problem and you can just go and hopefully you could just solve the easier problem right off the bat, but you might need to cycle this again. You know, you might need to do rational root theorem for that second thing that comes out of the synthetic division. Like you might get a cubed down here. Then you just, you know, go back, you look for another root, and you just keep going. So this is really where it comes from. So, you know, like we're used to seeing it this way, but like if you break this down, this specific cubic factors this way, okay? And the reason the first and last terms are so important are really just in how you multiply things out. If you multiply all this out, right, you do like, let's just take the first numbers here. So 3 times 2, you know, 6. Eventually you're going to do like 6 times 1, right? And it's going to stay 6. But that 6 is coming from the you know, part of the factors in here. Like the root out of this one, right, is negative 2/3. It's right there too. But the thing on the, you know, we're talking about having the structure like P over Q, and P comes from the end here, and we'll just say this Q comes from the beginning, okay? But basically Q is, you know, coming from here. It's the factors of 6, right? And that's like the 3. The 3 is one of the factors of 6. Also 2 is. But you'll see it better, I guess, if we did like the 5/2 or something, right? You know, out of this one. When we add 5 divided by 2, we divide by 2, and 2 is in the front, but then it ends up as sort of the bottom because of that, the way that division works there. And it's the same with the number at the end. If you do 2 times negative 5, you get negative 10. Eventually you'll do negative 10 times negative 2, you get 20. And so the factors of 20 will be, you know, related to the P, the, you know, the 5 or the 2 or the negative 2. So that's where it comes from. It's really just connected to the multiplication of factors and how you like double distribute or triple distribute here. So it's not really like a big magic trick, honestly. So let's just get into one and do one. So this is a cubic, and you know, just to kind of also tell you the order in which I would sort of want you to think about these problems. Way I would want you to think is I've got 4 terms, so maybe do factor by grouping, okay? But if you look at the ratio of the numbers, factor by grouping is not going to work, right? You can't take something out of 3x cubed and 13x squared besides x squared. So you're going to have like a 3x plus 13 left over. And there's no way you're getting like a 3x plus 13 over here. So you can kind of see just based on the numbers, like the ratio of 3 to 13 and 11 to 14 or negative 14. That's never going to be good for factor by grouping. So this is easier though, right? Like if for some reason you had 4 terms that would be nice with factor by grouping, that's what I would want you to do. You know, if for some reason like you had 3 terms like this problem, but you could do the substitution thing, you should do substitution. You only do rational root theorem if you've got no other options, okay? So my P over Q, P, factors of the last term. So factors of 14 are 1, 2, 7, and 14. And always positive and negative. Factors of Q, Q is, the factors of 3, the first term. So 1 and 3. And then, you know, I would always want you guys to try easy ones first, right? Like, I can check one negative one usually really quickly. Actually, let me just do it like this. You know, so if I check 1, you can just be like, okay, 3 plus 13 plus 11 minus 14. 3 plus 13 is 16. 16 plus 11, there's no way that's going to get me 0, right? Negative 1 is also pretty quick, because you'll have like negative 3 here, plus 13, minus 11, minus 14. That'll be what, 10 minus 11, negative 1, that's never going to be 0. So, you know, we just checked, we have also 8 options here, and we just checked we have 16 options. We just checked 2 of the 16 quickly, and I would always do these first, because you might just get lucky and have one of these be the correct root. But after that, you know, maybe I would try 2, negative 2, you know, if that doesn't work, 7, negative 7. I kind of go through those ones like first, like the nice integer ones, not the, you know, ones that truly have a like something besides a 1 on the bottom. Now this one, you might take a little while to find it, because if you just keep testing them, and you just do it on your calculator, you know, it's not something I write down. I just do 3 times negative 2 cubed plus 13 times negative 2 squared, right? You just do all that on your calculator. Eventually, if you do it out enough, in this one, you're going to get 2/3 as a root. So then we just go and, you know, so all I'm saying is f of 2/3 equals 0. And that's all just like calculator work, okay? You don't need to show that part out. You can just do it on a calculator and find it, and then this part you need to show out. So now we know we can divide 2/3 in, do synthetic division. In this case, we'll get a 2 here, a 15 there, 10 there, 21 there, 14 there, 0 there. This should have happened, right? Because if we don't get 0, then we're doing something wrong with our division. So then you just have 3x squared plus 15x plus 21. And actually, all these are divisible by 3, so you might as well do that. So really, you're going to have x squared plus 5x minus 7. Wait, was that a minus or plus? That should be plus, so plus 7. So this is the one that I'm going to now solve for my last 2 roots, right? So let's see. It does not look like it's going to factor. So I would probably just go and plug and chug quadratic formula. So do negative 5 plus or minus 25 minus 4 AC all over 2A. You're going to get plus and minus. You're going to get a minus 3 in there. So then you're going to have like I square root of 3 there, and then over 2. And that's it. So, you know, then just like circle all your answers. You got 2 roots right here, and then you got a root right there, right? So that is 3 roots. That's a bad 3. You got 3 roots, 4 and x cubed, which is good. And this is one where you really truly have to do rational root theorem. Like, you would not know any other way to do it unless you did this like kind of guess and check kind of thing, which is really what rational root theorem is. It's a little tedious. Like, the part that I'm not showing is probably the most work, to be honest. Like, finding that first root can be tiresome, but once you find it, then it's pretty quick, because then you just do your division. In this case, we're getting a quadratic, which we can just pop into quadratic formula for to get the other 2. But that is like a good example, basically, of a rational root theorem problem. So this last thing I just wanted to do is just kind of make sure you know when to use different methods. Okay, so I've got 6 different polynomials, and what I would want you to do is, you know, pause the video as always and try to think through which one here you would do with factor by grouping, which one you do with substitution, and which one you do with rational root theorem. And if none of these work for some reason, then there are technically other ways to do it, but they're kind of beyond the scope of our class. So these are the only three that you'll ever see in Algebra 2. So in my opinion, the easiest one to see is always this substitution one. So, it's actually, there's one right here. So substitution, you can always spot because you have three terms, and the first power is double this one, right? This is also substitution because it's three terms and 10 is double 5. So, here you would do the kind of thing where you're letting u equal x cubed, and here you're letting u equal x to the 5th. But those two are definitely substitution ones. And then this is not substitution because 10 is not double 2. And actually, kind of on that point, I guess, I don't have a good pink on here, so I'm going to do pink is blue now. For factor by grouping, you really need an even amount of terms, right? So you need to have even size, like the same size groups, I guess. So if you're doing like groups of 2, you could have an odd number of terms in your groups. You could have like 2 groups of 3 or something, but you still need the same size in the group. And, here you could do a group of 2 and a group of 1 or something, but that doesn't make sense. So, so this one is definitely like a rational root theorem. It's like a guess or check kind of problem. And then, for factor by grouping, what I'm basically looking for in these remaining ones here, because all these other 3 now could be factor by grouping, I'm basically looking for a ratio of the coefficients. So in the coefficients. So you can see here, 8 is to negative 64, the same way 1 is to negative 8. So that means that I should be able to do factor by grouping and get like a nice common factor in there somewhere. And likewise down here, right, 6 is to negative 16, the same way 21 is to negative 256. If you don't see it, let me just kind of start it, I guess. So you could take a 2v squared out, and then you would have 3v minus 8. And then in this next one, you could take a 7 out, and you'll still have 3v, and then you'll have minus 8. So that one is a little tricky maybe, but that one you definitely can do factor by grouping. But this one, if you look at the coefficients, there's no way. Like 1 to negative 1 means that this should be like, if this is negative 65, then this is 65. And that's not what's happening. So basically you'd have to do rational root theorem there too. So you really want to make sure you can like spot what to use when. Like it's super inefficient in your time if you always do rational root theorem. You want to like look for these two, like be on the lookout to do factor by grouping or substitution. And if those don't work, then you do rational root theorem. It's kind of your last resort because it is the most tedious one. And that is it. That is all I basically want to say about rational root theorem.